If you're an engineer, you know this feeling. That sinking feeling when something breaks, and all of a sudden, all eyes are on you to fix it. Well, today, we're going to walk through a classic production issue, from that very first alert all the way to the final fix, to really understand how a site reliability engineer thinks and works. So picture this. It's 3 a.m., the on-call phone buzzes you awake. Maybe it's a high CPU alarm, maybe memory is maxed out, or a health check is failing. You know what? The specifics don't even matter right now. What matters is something is wrong, and that clock, it's ticking. And this right here is the million-dollar question. Where do you even begin? Do you just restart a service and hope for the best? Frantically check the logs? Blame the network? Look, a panicked random approach is just going to make things worse. We need a method, a layered investigation that starts at the very, very bottom. So before we even think about a single server or a line of code, we have to ask the most basic question imaginable. Can anything talk to anything else? And for that, we've got to start at the foundation, the network layer. In our case, let's look at the AWS Virtual Private Cloud, the VPC. To figure out how traffic is flowing or not flowing, in AWS, you have to look at routing tables. Every single VPC has this special main routing table. Think of it like the default traffic cop. Any new subnet you create automatically uses this table to figure out where to send data. So our first check is super simple. Is this main table doing its job? Is it routing traffic correctly? And this brings up a classic interview question, one that's also a fantastic test of a core cloud concept. Can you just delete it? Can you get rid of the main traffic controller for your entire network? What do you think would happen? And the answer is nope. Not directly anyway. The whole system is designed to be resilient. A VPC literally cannot exist without a main routing table. So if you want to delete the old one, you have to first create a brand new one, promote it to be the new main table, and only then can you get rid of the original. It's a brilliant little example of how cloud platforms build in these safeguards. So, okay, our network seems stable. Let's move up the stack. All right. Check one, the network seems fine. So the next logical step is the machine itself. For this example, let's pretend our app is running on an Azure VM, but really the principles are exactly the same for an AWS EC2 instance. We just need to figure out if the server is healthy. Here's the typical playbook for a VM that's gone dark. First, you check the simple stuff. Are your network security rules, your firewall, blocking you? It's a surprisingly common mistake. If that's not it, you look at the boot diagnostics. This lets you peek into the machine's console as it's starting up. Is it stuck? Is it spitting out some critical system error like a kernel panic? And if all else fails, you take the final drastic step. You redeploy the entire machine. Now, let's be really clear about what redeploy means. This isn't just a reboot. Azure physically picks up your virtual machine and moves it to completely new, healthy, physical hardware. It is the ultimate fix for an underlying hardware failure on the host you are on. Could be a bad disk, faulty memory, you name it. But it does cause downtime, so it's absolutely your last resort. Of course, the real goal is to make sure one VM failing doesn't take down your whole application. And this is where high availability comes in. In Azure, you've got two main strategies. An availability set protects you from failures inside one data center, like a server rack losing power. But an availability zone, that's the gold standard. It spreads your VMs across completely separate data centers, each with its own power, cooling, and network. This protects you even if an entire building goes offline. Okay, so our infrastructure seems solid. The network is routing, our VMs are designed for high availability, so the problem must be higher up the stack. It's time to move into the application layer, into the Kubernetes cluster. In the world of Kubernetes, the most basic building block is the pod. You can think of it like a little wrapper, a little bubble around one or more of your containers. But the most important thing you have to remember about pods is that they are ephemeral. They are designed to be temporary. Kubernetes can and absolutely will destroy and replace them at any moment to keep the system healthy. So if pods can just vanish into thin air, what's keeping our application running? Well, that's the job of a deployment. A deployment is like a manager for your pods. You just tell it, hey, I want 3 copies of my application pod running at all times. If a pod dies, the deployment controller notices and instantly spins up a new one to take its place. That right there is the self-healing magic of Kubernetes. But, this self-healing creates a whole new problem. Every single time a new pod is created, it gets a brand new unique IP address. So, if your front-end service needs to talk to your back-end service, How in the world can it find it if the backend's IP address is constantly changing? And the solution to that puzzle is a Kubernetes service. A service gives you a single, stable IP address and a DNS name that never, ever changes. It sits in front of a group of pods and basically acts like an internal load balancer. Your other apps talk to the service, and the service automatically sends the traffic to a healthy pod, no matter how many times those pods get replaced or what their new IPs are. Okay, one last bit of theory before we roll up our sleeves. How does our app get its configuration? Kubernetes gives us two main tools for this. For stuff that isn't sensitive, like a port number or a feature flag, you use a config map. It's just plain text. But for the sensitive stuff, passwords, API keys, you must use a secret. Data in a secret is scrambled using base64, so it's not just sitting there in plain text. And even more importantly, it can be fully encrypted when it's stored in the cluster's database, which makes it the only real choice for anything sensitive. All right, theory's over. We've checked the network, we've checked the VM, and we've gone over the Kubernetes basics. Now it's time to consult an SRE's best friend, the runbook. It's time to finally run some commands. So we open the runbook for our service, and wouldn't you know it, it points to a very, very common problem, the dreaded no space left on device error. It looks like one of our servers has completely run out of disk space, and that's probably what's causing our application to fall over. So how do we prove it? The first command in our runbook is df-h. This stands for disk-free, human-readable. It just gives you a quick summary of all the mounted file systems and shows you how much space is used. We're looking for any line that's showing, 90%, or in our case, probably 100% full. Okay, so df-h tells us the var partition is totally full. But what inside var is the problem? This next command is a beautiful piece of command line magic to find out. First, du calculates the disk usage for every directory inside var. Then we pipe that output to the sort command, which puts the biggest directories right at the top. And finally, head just shows us the top 5. It's a super fast, super effective way to pinpoint exactly what's eating up all our disk space. We found the problem directory, and it looks like it's related to one of our containers, so the final check is to look at the logs for that specific container. The -f flag there lets us follow the logs in real time. We're looking for error messages, something that confirms the app is failing because it can't write to the disk. And there it is. We found our root cause. So we found the problem. We can now take the steps to clean up the disk, get the application running again, but you know what? The fix itself isn't the most important part of this story. The real takeaway here is the process we followed to get there. Let's just recap that journey. We didn't guess. We started with an alert, and we moved systematically from the bottom of the stack, the network, up through the virtual machine, and finally into the application platform itself. And by using a pre-written runbook to run a few precise commands, we found the root cause without wasting time. This methodical process, this is the core discipline of site reliability engineering. And all of this leaves us with one final thought. In a world of these incredibly complex, distributed systems, all running on layers upon layers of abstraction, it really makes you wonder, have we reached a point where building the initial software is actually the easy part, and the truly difficult, the real challenge, is just keeping it all running, resilient and reliable, 24/7?